So this video is an introduction to thermodynamics. So every object that you encounter, so my hand, this piece of paper, any object is made of atoms, which are often combined into tiny molecules, not always. These tiny atoms and molecules are always moving. So things that are moving have kinetic energy. And if they're atoms or molecules in a gas, then they're able to move freely. So you've probably seen pictures like this before. Molecules in a gas can go about anywhere they want. In a solid though, in a solid the atoms might be in like a crystal lattice like this. And we might think, well, how could they have kinetic energy? They're stuck in place. They can't move. Actually, they are moving. So they're just vibrating back and forth. So they're not floating about, flying anywhere like they are in a gas, but they are vibrating in place, just oscillating a little bit there. So they still have kinetic energy. They still have movement. A liquid is kind of partway in between a solid and a gas. So there's still a little bit of cohesion between atoms or molecules. They're still a little attracted to each other, but they're not like stuck together in a crystal lattice or something like that for a liquid. Alright, so if things have kinetic energy, then that actually also gives them their temperature. So temperature is actually just the average kinetic energy of those moving particles, of those little atoms or molecules. So a lower temperature means slower particles. It means everything's just moving a bit slower. And if things are vibrating really fast, bouncing around everywhere, that's a higher temperature. So fast particles, fast atoms and molecules is a higher temperature. To actually put a number on temperature, we need a temperature scale. So in the US they might use Fahrenheit, but we use Celsius here. So this scale, the Celsius scale, was named by Anders Celsius. It's named after him, and he based his scale on water. So that meant that he set the temperature water freezes to be 0 degrees Celsius on his scale, and the temperature that water boils at to be 100 degrees Celsius. So we sort of fixed those 2 points. So 0 degrees Celsius is freezing water, 100 degrees Celsius is boiling water, and then all the little degrees are nicely evenly spaced in between. So a scale is based off of water. In physics though, we often use the Kelvin scale. What's nice about the Kelvin scale is that it shifts where 0 is. So instead of 0 being where water freezes, 0 Kelvin is actually absolute 0. So that's the point at which the molecules have effectively stopped. They have effectively 0 kinetic energy. Now that can't actually happen in real life. So can't actually happen because of quantum mechanics. So quantum mechanics has a little thing called the Heisenberg uncertainty principle, which states that if you know an object's position perfectly, then you know absolutely nothing about its velocity. Basically, there's sort of like this interplay between an object's velocity or its momentum and its position. And the more precisely you know one, the less precisely you know the other. So if we were to say that the molecules have completely stopped, that's saying that we have a precise measurement of their velocity, an absolutely perfectly precise measurement of their velocity. It's exactly 0. And if we have a perfectly precise measurement of their velocity, we have an infinitely wrong or infinitely uncertain measurement of their position. And so we have absolutely no idea where our particles are in the universe anymore. So because of that Heisenberg uncertainty principle, we can't actually get to exactly 0, but we can get awfully close. There are places in the world where we've gotten down to 10 of a billionth, like 10 billionths of 0 Kelvin. So very, very, very tiny, very, very cold places. We do that in a really interesting method, actually using lasers. You might think lasers heat things up, but you can actually use lasers in an interesting way to very precisely cool down particles and make them move very, very slowly, which is cooling them down. So converting between Celsius and Kelvin is not too bad, and the reason why it's a fairly straightforward conversion is because the size of a degree Kelvin and the size of a degree Celsius is the same. So if these are sort of the size of your degrees Celsius, then your Kelvin scale is basically just like shifted over but the size of each degree is the same. So all you have to do to switch between the two is either add 273.1 or subtract 273.1. And zero, absolute zero Kelvin, happens when Celsius is at negative 273.15. So that's why we're going to be adding 273.15 or subtracting it. So say we have a lovely sunny day of 22 degrees Celsius and I want to convert that into Kelvin. I'm going from Celsius to Kelvin in this case, so I'm going to add the 273. So 22 degrees Celsius, I add 273.15, and that gives me 295.15 Kelvin. So that's my new temperature. So that's basically it. And if we're going the other way, we would subtract 273.15. Okay, thermal energy. So if average kinetic energy is the temperature, then total kinetic and total potential energy, so kinetic and potential, of all those atoms and molecules that are moving around in your object makes up the thermal energy. So that's two types of energy, kinetic and potential, and it's the total energy, not the average, whereas temperature is just the average kinetic energy. All right, so what does this depend on? Then let's sort of unpack what that means. So because the thermal energy depends on the kinetic energy, right? It depends on the total kinetic energy, but it does depend on kinetic energy in some way. Then that means it must depend on temperature, of course, because temperature is the average kinetic energy. So if you have a higher average kinetic energy, then you're going to have a higher total kinetic energy too, right? So your thermal energy will depend on that temperature in some way. Basically, if an object absorbs thermal energy, its temperature will go up, will increase. If an object loses thermal energy, then its temperature will decrease. It'll go down, be cooler. That's not all, though, that thermal energy depends on. It's more than just kinetic energy. So it's not just an average, it's a total energy. Because thermal energy is a total energy, it depends on the mass. So if you have maybe a 2-gram iron nail that's at some temperature, the temperature tells you the average kinetic energy of all of the little molecules in there or atoms in there. But if we have a 3-gram iron nail, we'll have the same average kinetic energy if it has the same temperature, but there's going to be more atoms in there. So if there's more atoms, there's more total kinetic energy. So that means it has more thermal energy just because it has more mass. So thermal energy does depend on what your temperature is, but it also depends on how much stuff you have, what your mass is, because it's about a total kinetic and potential energy, not just an average. The last thing that thermal energy depends on is the material that you have. And that comes down to the potential energy piece. So different materials store different amounts of potential energy in the attractive bonds between atoms and molecules that are in the object. So if you have like a solid, right, we talked about a solid that's often maybe in a crystal lattice, there's little attractive bonds between all of these little atoms here. And there's some energy stored in those. And as we vibrate, then we're accessing that energy that's stored in those bonds. So the thermal energy of your object will depend on what you're made of. One way to sort of summarize the material is using the heat capacity. So the symbol for that is little c, that's a lowercase c. And heat capacity is defined as the amount of energy you have to add to a specific material, whatever that medium is, in order to increase its temperature by 1 degree Celsius if you have a kilogram of the material. So it's just a way of summarizing something, a useful piece of information about your material. Okay, so that's what thermal energy is. How does it transfer from one object to another object? So if you put a hot object and a cool object together, the hot object will get a little cooler, the cool object will get warmer. They will transfer thermal energy from one to the other. It's basically two main ways. Conduction is energy transferred by contact. So that's when you have two objects that are touching each other, then the atoms that are moving quickly in object A bump into the atoms that are moving a little slower in object B, or molecules, and then that slows down. The atoms in object A lose a little bit of energy, it cools down, speeds up the atoms and molecules in object B, that heats it up, and you have thermal energy transfer by conduction. So you've all done this in the wintertime, I'm sure. If you're making yourself a cup of tea or a cup of hot chocolate, you put a cold spoon in your cup and you stir it around. you'll notice when you take your spoon out, it is hot, right? So how did it just get hot? Well, of course, it's because it was in contact with the hot water. And so the hot water, those fast-moving hot water molecules bumped into the spoon and sped up the little atoms in the spoon and got them heated up, got them moving faster, which is a higher temperature. The other way that energy is transferred is a little sneakier. It's by electromagnetic waves. And that's radiative energy. So all particles actually do emit some electromagnetic waves in radiant energy. So that's how an infrared camera can pick you up and pick up on your radiant thermal energy. But the sun is probably our most important source of radiative energy because that's what keeps the Earth warm. So the sun is not in contact with Earth at all. There's no conduction going on there. It's not like the sun is here and he just like cozies up to Earth every once in a while and gives us a lot of heat. Definitely no contact going on there at all. Earth is like way over here and there's nothing in between. There's literally a vacuum in between, absolutely nothing. So the only way that heat can get from the sun to the Earth is by electromagnetic waves carrying it. So that's radiative energy transferred from the sun to Earth, and that's how we warm up the Earth. It's with electromagnetic waves. Okay, so the quantity of heat. This is a way of measuring thermal energy transfer from one object to another object. And that's called the quantity of heat. So it's how much thermal energy gets transferred from object A to object B, or even just gets given away from object A. So if you're talking about just a single object, the quantity of heat is just how much thermal energy is lost or how much thermal energy is gained. Its symbol is Q, and because it's an amount of energy, its SI unit is joules, J. So if you're talking about, say, one object, when that object gains thermal energy, Q will be positive, and if that object loses thermal energy, its Q will be negative. The equation for quantity of heat, Q, is mc delta T. So it's going to be the mass of the object times its heat capacity times the change in temperature. And the change in temperature, remember, is always a final temperature, T2, minus a T1. So I could expand this equation to be mc T2 minus T1. That's my equation for quantity of heat, how much thermal energy gets transferred from object A to another object or just to the surroundings. So let's look at a case of an object transferring its thermal energy to the surroundings. So you do some cooking in your copper pot and then you just leave it cooling after you're done using it. So then it starts out at a really hot temperature because you were just cooking with it. So T1 is 130 degrees Celsius and it cools down to T2 is 21 degrees Celsius. During that process, we're losing energy, right? That's a cooling. So it makes sense that our Q should be negative. It's negative 50.0 kilojoules. That kilo is not an SI unit. I've got to switch that. So it's going to be negative 50 times 10 to the 3 is what kilo means. That looks kind of weird, so let's just put it in scientific notation. It'll be negative 5 times 10 to the 4 joules. There we go. That's Q. We also know the specific heat capacity of the pot is 3.8 times 10 to the 2 joules per kilogram degrees Celsius. By the way, these temperatures, you can switch them to Kelvin if you like, but you don't have to, because the size of a degree Celsius is the same as the size of a degree Kelvin. In this case, we're finding delta T, right, which is T2 minus T1. We're finding a difference between T2 minus T1. We're not looking for an absolute temperature. So because we don't have an absolute temperature, we're just looking at a difference in temperatures. It actually doesn't matter if you're in degrees Celsius or degrees Kelvin, you'll get the same result. All right, let's actually solve this thing. So Q is mc delta T. This one's a really straightforward one. We know Q, we know C, we know delta T. We're just solving for m. So we're just going to divide both sides by C delta T. That cancels C, cancels delta T, and I get m is Q over C. Delta T is T2 minus T1. Just expand that there. And then we can put all our numbers in. So Q is negative 5 times 10 to the 4. C is 3.8 times 10 to the 2. T2 was 21. T1 is 130. and then we'll just plug it all into our calculator. So 21 minus 130, 21 minus 130 times 3.8 times 10 to the 2, and then negative 5 times 10 to the 4 divided by that. That gives me 1.2. So the mass of the copper pot must have been 1.2 kilograms, and it looks like I have two significant figures because my heat capacity has two sig figs there. So that's my smallest number of sig figs. There's the mass. So when a warmer object comes in contact with a cold object, the two are going to exchange thermal energy until they reach the same temperature, thermal equilibrium. So if you have an isolated system, so this is like where you've got everything is insulated, so then there's going to be no heat lost from the system, no heat gained from the system. You have object A in here, and object B. Maybe object A is really hot, object B is cold, then there's going to be some Q released, some heat released from object A. This heat is being released here. And it's going to be absorbed by object B. So here, this is Q released. This comes from the hot object, so it's going to be negative. This will end up being negative. You don't have to like put a negative in there or anything, it'll just happen naturally. And that's because this object will cool. So in your delta T part, that's where that Q released will be negative, and this one will be positive. And that object will heat up. All right, so at the end of the day, they'll both be the same temperature. This one starts out hot, this one starts out a little bit colder, and they reach some temperature, not necessarily in the middle. It'll depend on the heat capacities of the object and the masses of them, where you end up. So here's an example. Let's say you have a bucket of water. There's 0.1 kilograms of water in here, and we're going to put a little bit of iron in there. And this is a closed system, so we're going to assume there's no energy lost to the surroundings. This is a really well-insulated bucket. Let's write down everything we know here. So we're given the mass of the iron. Mass of the iron is 32 grams. I need to switch that to kilograms, so 0.032 kilograms. I know the mass of the water is 0.1 kilograms. I know the initial temperature of the water, so T1 of the water is 20 degrees Celsius, and I know T2 of both the water and the iron is 22 degrees Celsius. So the water will heat up to 22 degrees Celsius, the iron will cool down to 22 degrees Celsius. And the last thing that I know is the heat capacities of both the water and the iron. So the water has a heat capacity of 4.18 times 10 to the 3 joules per kilogram degree Celsius, and the iron has a heat capacity of 4.5 times 10 to the 2 joules per kilogram degree Celsius. Okay, we want to know, so our required is the T1 of the iron. That's what we're wondering. Well, let's start out by setting up our general equation for thermal energy transfer. So Q released plus Q absorbed all adds up to 0. So this adding up to 0 thing means basically all the energy released from the iron is going to be absorbed by the water, and there's nothing left over. There's sort of 0 left over. That's kind of what that equation means. So iron is the thing doing the releasing, and water is doing the absorbing here. That's because iron is cooling down and water is heating up. So it's gaining the energy and iron is losing the energy. So let's write out our equation here. So that this will be the mass times C times delta T, but it's the mass of the iron, C of the iron, delta T of the iron. This is the mass of the water, C of the water, delta T of the water. And that all adds up to 0. We can expand this a little bit, so this will be mass of the iron, C of the iron, T2. T2 is the same for both of them, so I don't need iron or water subscript there. And then T1 of the iron. This is mass of the water, C of the water, T2 minus T1 of the water, and it all equals 0. Just put the 0 on this side. I'm trying to solve for T1 of the iron, so it's probably a good idea to expand these brackets, so I'll do that. So I get 0 is mass of the iron, C of the iron, T2, minus mass of the iron, heat capacity of the iron, T1 of the iron, plus my mass of the water, C of the water, T2 minus T1 of the water. This looks messy, but it's actually not too hard to solve. I'm just going to move this term to the other side. It's negative right now, so it'll become positive over here. Mass of the iron, C of the iron, T1 of the iron, so mass of the iron, C of the iron, T2, plus mass of the water, C of the water, T2 minus T1 of the water. All right, my last move to get T1 on its own is just divide both sides by mass of the iron, heat capacity of the iron. So that cancels out here. You can divide the entire side by MC here, or you can do it term by term. And I kind of like the idea of doing it term by term here, just because then it cancels nicely on that term. Doesn't cancel on this term, but it just looks kind of pretty that way, I think. And I get T1 of the iron is just T2 from this term, plus all of that. So I'm going to actually just plug in my numbers right at this stage. So T2 is 22 degrees, and then mass of the water is 0.1. Heat capacity of water is 4.18 times 10 to the 3. T2 is 22. T1 of the water is 20. All divided by mass of the iron is 0.032. And heat capacity of the iron is 4.5 times 10 to the 2, and that's it. All right, so plugging this into my calculator, I'm going to start with this bracket here. So 0.1 times 4.18 times 10 to the 3 times 22 minus 20 is just 2, divide by 0.032, also divide by 4.5 times 10 to the 2. And I get 58, and then plus my 22 here. It's going to give me 80. So T1 of the iron is 80. Looks like I've got 2 sig figs, so that's perfect. 80 degrees Celsius. And that is it.